All right, so one of the main goals of every chemist in the production field is to try to produce a compound that's new, that's novel. You want to make something new and you want to put your stamp on it, and then you want to sell it and make millions and millions of dollars for your company, most likely. And when we do this, we produce something that's probably never been produced before. Maybe a new medication, or maybe a new type of plastic, or maybe a new material for electronics. When we're coming up with new materials, we don't actually know the identity, the specific identity of those materials all of the time. So we need some technique to try to figure out what particular materials are made out of when we first produce them. And it's the job of the chemist to do this. So there's two big tools that we need. We need to know which elements are present, number one, and we also need to know how many of each element is present in the molecule. So those are the two questions that we're going to have to try to answer as chemists. Luckily, we have some instruments that tell us the masses of elements in the sample. We have a neat little instrument called a gas chromatogram, and this is a picture of one of these things. We have a material that we've maybe produced in the lab, and we put it into the gas chromatogram, into the sample injector. And as you follow my green mark here, you'll see that sample actually follows these circles, these coils that are inside of the oven, and that actually bakes the material. It heats it up to a really high temperature, and as it's flowing through the coils, then it actually turns into a gas, and it passes through a detector, and the detector is able to detect what elements are present in your original sample. And that detector then sends that information to a little printout, and that printout tells you what types of elements were present in your original material. So maybe you had 1 gram of material that you put into the detector, and the detector told you that, well, we had some carbon, and the carbon was 0.25 grams, and then the hydrogen was 0.50 grams, and then the oxygen was 0.10 grams, and then finally the nitrogen was 0.15 grams. So you would know the makeup of your original sample. Now, it's our job in this section to be able to take this data right here and use it to find the actual formula for the compound. Just like we know the formula for water is H2O. We know the formula for hydrogen peroxide is H2O2, or ammonia is NH3. We want to know the formula for that compound. With this data, we're going to be able to find that formula, and that formula is going to be called an empirical formula, and here's a definition for that. It's the formula of a compound expressing the smallest whole number ratio of atoms in a compound. And to do that, to find that, we have to follow some steps to determine this empirical formula. And here are those steps. You can pause the video and write those down. I'm going to skip through them right now. And let's skip to our first example. So let's assume that we make something new, and we know that the detector tells us, well, there's aluminum in there, and then there's oxygen in there, and the detector tells us how much aluminum and how much oxygen. And if you refer back to those steps, you're going to understand that we have to take those masses and we have to turn them into moles, because as we have learned, atoms don't combine according to the mass of each of them, but they combine according to the amount of each of them. And so that's why we will convert into moles. So how do we do that? Okay, well, let's take our mass of aluminum, and we're going to use the molar mass of aluminum, which we get from the periodic table, to turn it from grams into moles. So the molar mass of aluminum is 26.98 grams per mole. And watch how I write that into my formula. I'm going to put 26.98 grams in the bottom of my ratio and 1 mole on top. Why do I do that? Well, if I do that, then grams cancels out nicely. There we go. That looks good. Now, if I pump that into my calculator, I'm going to find that the number of moles of aluminum atom is 0.1539 moles of aluminum atoms. Okay. Now, let's do the same thing for oxygen. Okay, I'm going to take the molar mass of oxygen, which is 16 grams in 1 mole. I'll do my calculation there, and I'll find out that there's 0.2308 moles of oxygen in that original sample that I injected into the gas chromatogram. Now, step 2 of the process says to take the smallest number, the smallest amount of moles, and divide that by each of the elements present. This is like we're finding a relative mass, like we did with the hardware example. So I'm going to take each of these and divide them by 0.1539, divided by 0.1539. And when you do that, for aluminum, you're going to find out that, well, okay, aluminum equals 1. Let's do the right symbol for aluminum, right? Aluminum equals 1. And for oxygen, it's actually not going to equal 1. Instead, it's going to equal 1.5. Now, if you go back to your rules, if any of these numbers at the end of the day, if any of these numbers don't come out as whole numbers, you have to multiply it by the smallest whole number that will make these numbers whole numbers. So that's going to be 2. If I multiply by this by 2, and that by 2, 1 times 2 we know is 2. 1.5 times 2 is 3. And that actually tells us the subscripts that are present in our empirical formula. So this oxide of aluminum has a formula of Al2O3. Where does that second 3 come from? Right? That 3 is the same as that 3, right? Alright, so that's my formula, Al2O3. And that's an empirical formula. Now, the empirical formula gives us the lowest ratio of elements involved in a compound, but different compounds, we can have differing compounds that actually have the same exact empirical formula. This causes an issue, and I'm going to give you an example of why this is an issue. So let's look at these two things, CH2O and C6H12O6. If you reduce these two things, okay, you can't reduce the one on the left. You can't do that at all. It's in its lowest possible form, 1, 2, 1. But you can reduce this guy. You can reduce this. The carbons would cancel out. The hydrogen would only, or I'm sorry, the 6s would cancel out. The hydrogen would go down to 2. So you would see that their empirical formulas would be exactly the same. But as we will see, these two things are totally different materials. Totally different materials. CH2, its common name that you might be aware of is formaldehyde. Now, formaldehyde was the chemical that we used to put like brains and specimens of the human body, and when we would embalm humans to show them at funerals, we'd use formaldehyde to preserve the body. It's a great preservative. We don't really use it anymore because it's actually a carcinogen, so it causes cancer, so we use other things. But as you look at the picture of the brain in the case here, it's actually sitting in a bath of formaldehyde. It's incredibly bad stuff. If you'd take formaldehyde in, you'd probably not make it very long. Now, C6H12O6, that is something entirely different. That is something called glucose. Glucose. Now, glucose is essential to human life. It is really one of the fundamental building blocks for energy in the body. And I use these packets once in a while. If I go on a long run, or if I'm competing in a run, I take these gel packs with me because they have glucose in them. And if I eat that pack, it gives me almost instantaneous energy. So my goodness, you totally see the difference between these two compounds. Boy, if I asked for some CH2O and somebody wasn't aware of the fact that we needed to separate out the two empirical formulas of these two compounds, maybe they'd give me formaldehyde, and I'd be eating formaldehyde while I'm running, and that would not be good. I don't want to do that. So we need something else, some other tool, and that's what we call the molecular formula. The molecular formula is going to actually be the actual formula, not the reduced formula, not the lowest ratio of elements involved, but the actual formula of a compound giving types of atoms and the numbers of each type of atom. In order to figure out the molecular formula, we need another piece of information, and that is the molar mass. In order to figure out the molecular formula, we need the compound's molar mass, right? There should be an apostrophe right here. I got to get my English right. Okay, and we have another tool that can give us that called a mass spectrometer. All right, so let's see how we can use a molar mass to figure out the molecular formula of a compound. We've got a white powder analyzed, and we know that its empirical formula is P2O5. Maybe we did the same process that we did for the previous empirical formula example. We then use a mass spectrometer to find that the molar mass is 283.88 grams per mole. We want to know the compound's molecular formula. This right here is the lowest ratio of the elements involved. We can't reduce that anymore and still take whole numbers. So that is referred to, again, as the empirical formula, as you see right here, right? Okay, so now we want the molecular formula. So what we've got to do is figure out, well, P2O5. What's the molar mass of that? We're going to call that the empirical formula, molar mass. So the empirical formula, MM, that equals the molar mass of phosphorus times 2, okay, molar mass of phosphorus times 2, which is going to be 61.94 grams per mole, plus the molar mass of oxygen, 16 times, what? 16 times 5, yeah, and that's 80 grams per mole. Okay, let's add those two up and see what we get. We're going to get 141.94 grams per mole. And again, that equals my empirical formula, molar mass. Now, we want the molecular formula, molar mass. So what do we know? Well, we know the molar mass of the molecular formula. We need to find out what that exact molecular formula is. So we're going to take the molar mass of the molecular formula, which is this guy right here. Let me change my marker. This guy right here. 283.88. And we're going to put that over the molar mass of the empirical formula, 141.94. And we see, hopefully, that the molecular formula is twice the empirical formula. So that means we come up here to our original empirical formula, and we multiply all of our subscripts by 2. So our final result is P4O10. That is our molecular formula. Bingo! Ha! We just found our brand new product, which we're going to sell for millions of dollars.